All right, I'm trying something a little new tonight when it comes to the slides. I got everybody into Jupyter Notebook last week, and so I spent today, or this week, getting ready for tonight's lecture, focusing on Numpy, which is a Python library that we will be using. It's kind of foundational to anything we do that's like data analysis. And so tonight's Numpy examples are all going to be in Jupyter Notebook. And one of the neat things I found, which I didn't know before, was that you can export a Jupyter Notebook as a slideshow. So we're going to be going through that. I may flip back and forth between the slideshow and the actual notebook as we, if we want to talk about stuff. But for now, let's get going. This material, where's my book? Comes out of the Python data analysis book. That camera. Chapter 4 is where we're going to be focused on today. How do I do this? There we go. Numpy is a numerical Python library. The core library built to handle data, arrays of data, multi-level arrays of data, all that kind of stuff. It doesn't do its own scientific or any numerical analysis. But it is used as the backbone for all of the other packages we'll talk about, like pandas and matplotlib and IPython, whatever else we get to this semester. So what we're going to be going over is going to look like a lot of math, and it'll feel like a lot of math, but I think we'll get a good understanding of it after we go through tonight's slides. If you want to follow along, you are welcome to. If you open your Jupyter Notebook, as usual, one thing I think we talked about a little bit was the environments within Jupyter, or within Anaconda. And so you'll see I have an environment up here called Info 410 Fall 2020. When I do this Numpy stuff in Anaconda Navigator, I have to manage my environments. And I select my environment. I look for the uninstalled packages, and I need to install Numpy. So right now I'm showing you the picture after I already installed it. But if you don't have it installed, you change this drop down to look for the uninstalled libraries. You can search for the name Numpy and go through the installation there. So this is the package management and virtual environment concept within Python. So once we have Numpy, the primary data object we're going to be talking about is the ndarray. It's a efficient multi-dimensional array. It provides fast arithmetic operations. It allows you to process all the data within these arrays without having to write for loops or anything like that. So it gives you this high-level stuff. There are also tools for reading and storing this data on disk in a really efficient way. So unlike Python normally, when we create a NumPy array or an ndarray, we allocate a certain amount of memory for it, and all of the data is stored in a contiguous memory block, which makes it a heck of a lot faster than a normal Python array. And also you can integrate NumPy with a whole bunch of C libraries, system libraries on your computer written in C, C++, and Fortran. So when you want to write your Fortran libraries, you're welcome to. But you don't have to do that. So when we start in our Python, this is one cell within a in a Jupyter Notebook. And the first thing we need to do is get access to the NumPy library. So once we have it installed, like any other library, like the system or the OS or the requests library, we can import the NumPy library. And for whatever reason, everyone seems to always alias NumPy as NP. I think they just don't want to type NumPy over and over again. They just want to write NP. So if we didn't use that as NP alias, all of the functions that you see us that we'll be getting to, we would have to write out the full library name, which is NumPy. But since I'm aliasing it with that as keyword, we can get reference to all the functions and whatnot using the NP alias. So once we import it, we can do a whole bunch of different stuff. So the main, I guess the main object, the ND array that we'll be using, is created and managed by Numpy, and there are going to be a whole bunch of different ways we can create those. One of those ways is by accessing the random components of Numpy. This is a different random implementation than the Python library itself. It's supposed to be more random, who knows? But we reference it like NP is the Numpy library, .random, which is a package, and a function rand_n. And here we give it a couple of parameters, 2, 3. So what we're going to be building is a 2-dimensional array where we have 2 rows, and each row has 3 columns or 3 attributes. It's really a nested list, so that the top level will be it's a 2-dimensional list. Each element in the list is another list, and the secondary list has 3 elements. So when we look at what that looks like when we print it out, we can see that we have some random values. The first list has 3 elements. The second list also has 3 elements. So this is a multi-dimensional array. And if you look closely at the notation, you'll see there's a list annotation, and inside of that list is 2 other lists. Remember, lists can store number strings, nuns, other lists, anything. So this is a list of lists. We can do fun math very simply. See, I'm not writing a for loop. I'm not calling any functions that look special. I want to multiply every item in this array by 10. And you'll see my output here. I get negative 4.6, which is 10 times negative 0.46. Each element in all of this, in all of these lists, I guess is a good way to say it, in this matrix, are multiplied by 10. That simply. So when we talk about fast arithmetic operations, that's what things like this mean. I can affect every item in the array without looping. I can add 2 arrays together. And what this does is another arithmetic relationship. And if you think about the data inside these arrays as a grid, right? In this case, we have 2 rows and 3 columns. So the first row has elements 0, 1, and 2. The second row has elements 0, 1, and 2. When we add 2 arrays together, it takes the 0, 0 element and adds it to the 0, 0 element in the second array. And then it moves to the 0, 1 element and adds it to the 0, 1 element of the second array. So in the end, you end up with one array, but with the matching values all added together.
So this is temporary, correct? If we wanted to assign data to be equal to data plus data, we could do that, but this is temporary.
Temporary is a good word for that, yes. But yes, you could assign this to a variable. So if we jump to the code here, where I'm doing my data plus data, let's do a quick row insert. I can make a new variable equals data plus data. And when I run that, I will output it. So same math, but now I have a new array. And so let me show this a little bit differently. Let me do this a little bit differently. Same concept. I'm going to make second array is data times 10. And I'll output second array. So it's this annotation here. After that, I will output data, which was my first array. and then I will output second array plus data. All right, having it all on one screen is going to help, I think. So I have two arrays that I'm dealing with, second array and data. They're each 2 by 3, 2 rows, three elements in each row. Everybody got that? Okay. When I'm adding the 2, I'm adding this element, the 0, 0 element, which is negative 4.62, etc., and the 0, 0 element of the other array to combine to be, what, about negative 5. And so I get negative 5 in the new resulting array in the same 0, 0 spot. I add the 0, 1 spot in both, and I should get in the new 0, 1 spot negative 1.4, which is negative 12, negative 0.129, etc., plus negative 1.29. I don't know why they're all negatives, but they are. So when we add these arrays, we are not like adding all the values in the array into one number. We are positionally adding the two arrays together. Does everybody get that? Because that's super, super important for everything else we're going to talk about tonight. Okay. I caveat real quick. I am a strong math nerd, but I'm not a super math nerd. I did not major in math. We will get to math that I do not understand. And that's okay, hopefully, because you don't have to understand the math either. The important things are these functions and how we operate on these arrays. All right, going back to the slides. There is a attribute called shape on the array, and the shape tells you the attributes are the size of the array. So in this case, again, it's a multi-dimensional array, 2 rows. Each row has 3 records, columns, whatever word we want to use. There's also a data type associated with a array. It is a kind of a metadata thing. It just kind of, the way Numpy works is, it looks at the data that is in the array and keeps track of it. So when I see this row, the data type of this array is a whole bunch of float 64s. They're 64-bit floating point numbers. So 8 bytes of memory per element. That's important when you think about, again, how the Numpy library allocates memory. So when we have a 2 by 3 array, how many data points will we have in that 2 by 3 array? Two rows, 3 columns each. It's 6. Nobody's answering, but it's 6 because you have 3 per row, and there are 2 rows. So the second part in figuring out how much memory to allocate for these things is what is the data type inside. And we'll talk about all the data types we have available, but for the math behind it, a 64-bit number is 8 bytes of memory. 8 bytes of memory. 8 bytes times 6 fields is 48 bytes. So when I create a new array, the processor or the Numpy library allocates 48 bytes of memory contiguous, all together next to each other. And it knows, based on the data type size, where in that memory each element is. That's how it's efficient with the memory. That's kind of computer sciencey. Note from the book, they are not consistent, and I won't be consistent. They call an ndarray multiple different things. They'll shortcut it and just say array. They'll shortcut it and say numpy array or ndarray. When we're talking about this context, any of those words work. So hopefully I don't confuse you. All right, all the ways to create these arrays. We can create them from a list. So this first line is a regular Python list. Whoop, where am I? There we go. A regular Python list with 1, 2, 3, 4, 5 elements in it. The NumPy library has an array function, and if the parameter is a list, it knows what to return. Oh, I did this wrong. Okay, I'm going to go back to my Jupyter library. The output hasn't run the code yet. It's just the code. So let's go back here. Okay, so here, we'll run that. The list is created. Then I create an NP using the NP array function. I assign that new array to ndarray underscore data1, and then I can show you what that looks like. It is a new array, and that array contains a list of the items that were in the original list. Anyone want to guess what the shape of that array will be? Remember, the first one was 2, 3 because it was 2 rows, 3 columns. One comma 5, I think. 5 comma. I guess because it's not multi-dimensional, it's just 5. I would have guessed 1, 5 as well. And the data type. So we haven't talked about the data types, but I have a mix of floating point numbers, integers. So the data type is going to be some sort of float. Float 64. To create a multi-dimensional array, again, I have 2 lists in this case. I'll run that, and I will output it. 1, 2, 3, 4, 5, 6, 7, 8. Anyone want to guess the data type? It's some sort of integer, I bet. I hope. So it's a 64-bit integer, because they're all integer numbers. Ndim. I totally forget what ndim does. Let's figure it out. 2. The return from ndim is 2. Something dimensions. So I think that's the first number of arrays. So it's a 2-dimensional array. ndarray.shape. Anyone want to guess on that one? Two, 4. There we go, 2, 4. All right, so I already said this, but the data type is inferred. Are y'all following okay if I'm doing it with Jupyter Notebook like this? The 2 ladies I can see said yes. Another yes. Yes. Cool. Okay, good. So I'll stay here until I don't want to. NumPy has a suite of functions for creating new arrays. So there are different ways of doing this. The first function we'll talk about is zeros. np.zeros 10. Anyone want to guess what that will do? I like guessing. I like putting you on the spot. Yeah, that's my guess. A single dimensional array with 10 zeros. Single dimensional array with 10 zeros. np.zeros The parameter is a tuple 3, 6. What do you think that'll give me? A 2-dimensional array with 3 rows, each with 6 attributes, or 6 columns. This is a fun one. Zeros. I think there was a ones equivalent. Let me do np.ones 3, 5. It'll be all filled with ones. np.empty 232. Ooh, what's that going to give us? I don't remember. I'm going to hit run and see what happens. This feels like a 3-dimensional array. This is a 3-dimensional array. But notice the values. They're kind of garbage. 2.058335592 e to the negative 312th.
So I did the same thing in my Jupyter Notebook, and I got all zeros.
Yeah. In the book, it says you get all zeros. But then it has this little note that says, it is not safe to assume that np.empty will return an array of all zeros. In some cases, like mine up here, it may return uninitialized garbage values. Uninitialized garbage, my note was whatever was already in memory. So, going back to the math a little bit from earlier, let's assume this creates, yeah, they're all floating point numbers. This creates, by default, float 64. Float 64, yeah. Each float 64 is 8 bytes of memory. This is a 3-dimensional array, 2 by 3 by 2. So if we multiply 2 by 3 by 2 is 12. So there are going to be 12 elements. Each 8 bytes. It's 96 bytes of memory. The way the memory allocation works in a low-level programming language, it just the operating system assigns this code 96 bytes of memory. It doesn't automatically clear them. It doesn't set them to 1. It doesn't do anything. It says, okay, nobody's using this memory. It's all yours. So when we do that, for whatever reason, some implementations of Numpy, like on Caitlin's computer, sets them all to 0. Are you running Windows? Yeah. And on my Mac, it doesn't do anything, and it just gives me whatever the memory is in that memory address. So the point of that warning is, if you write this in your code, and it's not just a big multi-dimensional array, if you allocate any memory, if you create an array with the empty function, you cannot guarantee the data in there means anything. You need to default it. And there are a bunch of different ways you can do that. If you want zeros, use the zeros function. If you're going to read a file, the next step, you're going to read a file with a whole bunch of data and put it right in here. Write the data before you read the data. Okay, another cool function. We've used the range function, right? The regular Python range function. It essentially returns a list of integers, in this case 0 through 9 inclusive. I'll run that, and so I can print out 0 through 9 inclusive, 0 through 10 exclusive. There's something very similar for NP, for NumPy. There's an arange function, and the parameter is the same, but in this case the return value is going to be a Numpy array, but the data will be pre-populated. What do we think the data will be pre-populated with? It's really similar to what range does. It'll give us an array where the values are 0 through 15 exclusive. But now we have an ND array, a Numpy array that we can use. So there's a bunch of them. Oops, didn't mean to double click that. There's an array, there's an as array, a range, ones like, is a function that takes in a parameter of another array, and it makes a new array of the same shape as the old array. All the likes do that. So ones, zeros, empty, full. I don't know what full does. Let's figure out what full does. Oops. Add. Yeah, you go down there. np.full. Oh, missing a positional argument. We learned about positional arguments last week. Maybe this is what it is. And every value will be set to 0 or 100. So doing np full with a 0 is exactly the same as the zeros function. But I can do whatever I want in there. So it'll fill every memory spot in that new array with that default value. NPI. So these I in identity functions, I don't know why we would use them, but they are kind of cool. Maybe y'all are smarter than me and can figure it out. NPI 12 makes a 12 by 12 array, and for whatever reason, it sets the diagonal in the middle to ones. Every other value is 0, except for that diagonal top left to bottom left is a 1. Maybe there's some math reason to do that.
It reminds me of linear algebra a lot. I can't remember what exactly, but looking at it,
does it?
Reminds me. It does, yeah.
Okay, that might be it. So that could be a linear algebra thing. Again, I know I'm good at math, but that's like that's too much math. I think identity did the same thing. Yeah, it did the same thing. So if you need a multi-dimensional array that is preset with sizes, and a diagonal ones, then that's how you can do it. You can explicitly tell an ND array of what data type to use or to have inside of it. So same creation, NP array, I'm passing in a list, 1, 2, 3, and my data type, I want a float 64. So D type, so my keyword argument that we talked about last week, D type, I'm assigning the value NP float 64. So then that gives me an array with 1, 2, 3. But since you see the decimals here, you know they are floats. I can call that dtype function, or get that dtype attribute from that array, and it'll confirm it is a float 64 data type. Int 32 is another data type. You can see my int 32 is a data type here. I'll run it and see int 32. So because of the math of memory allocation we talked about earlier, a 3-element single dimensional array where each item is 8 bytes or 64 bits, we know this allocated 24 bytes of memory. When I do the same thing with an int 32, each integer is only 32 bits of memory and 4 bytes. 32 divided by 8 is 4 bytes of a 3-dimensional array. So this is a 12-byte data structure. This is a 24-byte data structure. When you start dealing with really, really large data sets, that can start to matter. Essentially, I can have an ND array of integers with twice as many numbers in it, in the same amount of memory as so if in the same amount of memory for something half the size if it were 64 bits. So if we start doing statistical analysis of very large data sets, we could start running out of memory if we allocate too much memory per data field. Here's a bunch of different data types that are supported in Numpy. Integers, either 8, 16, 32, or 64-bit. You do not have to memorize this chart. There are floats, 16, 32, 64, 128-bit floats. You have complex numbers that are either, like golly day, 64-bit, 128-bit, or 256-bit. What a complex number is, it's really two numbers being memorized or being stored. So it's two 32-bit numbers, two 64-bit numbers, two 128-bit numbers. Boolean, object, string, where a string is an ASCII, a list of ASCII characters, or Unicode, which is a list of Unicode characters. Unicode characters, I believe, are 64-bit characters, where an ASCII character is a 8-bit character. Everybody with me so far? I know this is kind of dense tonight. We draw pretty pictures below, so we'll get to the pretty pictures soon. Charts and graphs are fun. We can convert the data types. So if I have an NP array of integers, 1, 2, 3, 4, the data type is an int64. I can convert it by taking that array, my int array, calling the asType function, passing in the new data type, and the output is the new array. That does not change my original array, but it takes the whole memory space, reallocates the new memory based on new data type, and copies all the values. And so that new float array has a new float64 type. There are a ton of more ways of getting slices out of that out of the array, like we talked about the lists and getting list offsets in the 1st through 4th element, the 7th through 12th element, all that kind of stuff. You can do all that in these arrays as well. Chapter 4.1 in the book talks about that. Read it. I don't want to go over it tonight because it's very repetitive from what we've done. So you reading through it, you should be able to pick it up quickly. And if not, email me and we'll go through it. So if you convert a float to an integer, will it truncate? Is that what you asked? Probably. Let's find out. So I have a float array. So Caitlin asked, if we take a float array and convert it to an int array, will it truncate the, I'll fill in the words, truncate the decimal, right? And I'm confident that it will, but we will find out. So let's make a new float array. Is a Numpy array, and I want the values of, array 1, 4, 1, 2, 3, 10, whatever, bunch of numbers, and then I'll print it out. New float array. Okay, there's my new float array. Now I want my new int array equals new float array. What was it? As type type np.int32. So I'm specifically even cutting down the memory allocation for it. I'm not doing a 64-bit integer. That's my point. And I will run that. Oop, and it ran. And I want to print that out. And so yes, it truncated the decimal off of every number. So it floored all of the floats and then turned it to an integer. Great question. So there are two types of functions for these arrays that we'll talk about. The unary functions act on that one array. So these are things to do with a single array. So you can do things like calculate the, I need to stop double clicking on that. Calculate the exponential of each number. Calculate the square root of each number. Take 2 to that number exponent, absolute value, square value, log 10, etc., sine, ceiling, all these mathematical functions that we can do in this array, in these arrays. But again, these are single unary functions. So as an example, I have a new int array2, which I created with the arange function with the value 12 and my data type. So here I can explicitly tell it what data type I want on creation as opposed to it figuring it out. And we can see that I got a 0, 1, 2, 3 through 11 like I expected to. Now I can run these different functions. So the exp2 function, where for each item in the array, it will raise 2 to that power. Okay, so it took 0 and raised 2 to the 0th power, and we all know anything to the 0th power is 1. It rose 2 to the first power and got 2. It rose 2 to the second, got 4, 8, and then it just gets bigger math. So these are big floating point numbers, and it's scientific notationing them because they're too big. And so I don't like that because I can't read it as well because they're all floats. I'm going to do the same thing, np exp2 int array2 as type np int32. This is probably not terribly efficient, but this will give me the numbers that I actually am looking for in a human readable fashion. 1, 2, 4, 8, 16, 32, etc. So I'm kind of chaining these things together, and what Numpy is really good at is making them fast. Question earlier, we were talking about truncating. If a decimal is 0.5 or higher, will it automatically round up to the integer, or no? No, it will not. That is rounding. That is not truncating. Truncating is if you imagine any number like a 3.14. Anything after the decimal is just dropped and ignored. It doesn't matter what was there. 3.99, 3.98, 3.14, 3.16, all the point whatevers just gets dropped off because it's only looking at the integer value. It should be the same as doing the floor function. So we could play around with all these. So yeah, there is actually a floor function in there as well that we could do. I don't think there's a round though. There's not a round. Logs is number, all cosine, arc cosines, etc. So you can start thinking about doing mathy kind of stuff with this. Binary functions takes 2 arrays to deal with. So you can add, subtract, multiply, divide, floor divide. Find the maximum number, the minimum number. And again, if you think about each spot that matches the other array's spot, when we do a maximum or minimum, we're comparing those 2 spots alone. Copy sign takes the sign of the second array's spots and puts it into the first, which is an odd function, but maybe that's another math thing. Greater, equal, less, lesser, equal, logical and, ors, or XOR. And so here's the experiment. So we will make two arrays, first array, second array. I put the same values in both, 1, 2, 3, and 4. When I add them, what will be my resultant array? Yeah.
4, 6, 8.
2, 4, 6, 8. It's a one-dimensional array, 4 fields or 4 spots, and yes, those would be the values. 2, 4, 6, 8. So it took this value, added it to this value. The 2 added it to the 2, 3, 3, 4, and 4, and added them together. So the resultant array is of the same shape as the two inputs, and it adds the values. So here we'll subtract. We have first array 1, 2, 3, 4, second array 10, 20, 30, 40. I will subtract the second array from the first array. So my results should be -9, -18, -27, and -36, I think. Yep. Subtracting the second from the first. Again, resultant array is the same dimensions, the same shape. What if the arrays are a different length? Will you get an error? I don't know. Let's find out. Let's take my two arrays here. And I'm going to add a couple of values on this one. And see what happens. There you go. I got an error. And my traceback tells me exactly where it happened. Operands could not broadcast together with the shapes because they're different shapes. Great question. Oh, and so then the reverse, I can subtract first from second. Oh crap, but I changed those. So I will take those out. Actually, no. What I want to do, I want to keep those in case someone looks at this later, because I will update it. So I need to run this again to get my two arrays. Do my weird second one. And okay, then I'm going to subtract the first array from the second array. So now I should have my positive numbers. So again, it was 10 minus 1, 20 minus 2, 30 minus 3. So the order of those arrays matters. And again, it does not change those arrays. The result is a new array. But you can store that in a variable. In this case, third array. It jumped on us. So I saved it in a third array variable, outputted third array, and we got those values in a third array. They're all different memory, they have all different values in them, but they are all of the same size. Man, I've only been talking for 45 minutes and we got this far. I wasn't expecting this. Looks like we'll get some hacker rank later. Any questions up to this point? Because next I want to show you some stuff we can do with it. All right. So now we have another library to install into our Python environment, or our Anaconda environment, called matplotlib. Mathematical plotting library? I don't know what MAT stands for. What does matplotlib stand for? Maybe it doesn't stand for anything. Anyway, matplotlib. So if you install that into your Python environment, same thing, look for the uninstalled libraries, search for matplot, and choose matplotlib, and it will install all the dependencies it needs. So we can do a whole bunch of fun stuff. Like NumPy, we can import anything from the matplotlib library. In this case, I'm going to import the pyplot library or package, and I'm going to name it PLT, so I don't have to type pyplot all over the place. So first, I'm going to create an ND array from my NumPy library. In this case, I will be creating the range function from -5 to 5 in 1/100th increments. So actually, I want to play around with that for a minute. I'm going to take that out here. I'll put that there. So I want to print out this points array. This is a big old array. It's a single dimensional array. But you can see the values go from -5 in 1/100th increments. Next, I'm going to make a grid. So np.meshGrid. Let's see what that does. I got copied and pasted this one. Let's see if it's in the book. Oh, if not, I'll Google. I have a feeling it's going to take one array or two arrays and do some sort of math on them. Page 110 in the book. Takes two one-dimensional arrays and produces two-dimensional matrices corresponding to all pairs of x, y in the two arrays. So it makes a whole bunch of combinations of stuff. So I'll have two-dimensional arrays when it's done. Is how I read that. So XS is a two-dimensional array. So it's x's and y's. So I'm going to be using these as coordinates in a plot. My z value is going to be the square root of x squared plus y squared. And so z, oops, I gotta run that first. Why isn't it printing that out for me? Oh, maybe this isn't done yet. There we go. Huh, that's odd. Whatever. So then I'm going to use that plot library, image show that z array in grayscale in a chart. So that doesn't really mean anything to us. So let's break that down into how we can actually build charts with Matplotlib. So I'll start with a new x's array. So in your head, visualize one array of our x points. And I'm going to plot them on a graph. So that's not really helpful. So, and power, yeah, that's all I'm doing. I'm just plotting that graph of those numbers. It looks like the x and the y value is the same. But if I want to try something, I think plot takes two arrays, the x value and then the y value. So this should be the same. That's the same. But if I add it together, Okay, cool. So now my y value, so the first one with just new x's, the x and the y value was the same. Now I'm taking the x values from new x, 0, 1, 2 through 9, which you see down here, and the y value is going to be the new x's array added to itself as a second array where the values are doubled. So my 4 value would be about 8. That's not really helpful either. Let's square it. So we have a power function. So we can raise every value in the x's to the second power. You'll see 0, 1, 4, etc. And we can plot that. So you'll see now, oh, the x value is the index. Duh, I knew that. Sorry, the x value is the index. And then the y value is the value in the array. And so the square, you'll start to see this exponential curve. And if we cube it, it'll go up even quicker. Much quicker. So we can start plotting these functions. So we saw a linear relationship with addition. That's why it confused me, because my indexes were the same thing. Let me unconfuse myself by doing this. There we go. Now I unconfused myself. So the index, this is a 0th index, this is a first index, second, or our x-axis, and the value is our y-axis. That's what it is. So then we cube it and it went bigger. Okay, we can format these graphs. So I'm going to run this one. I'm making another big range from 0 to 5 at 0.2 increments. And then I'm going to do some crazy plotting down here, which I will walk through in detail. So you'll see on this one chart, I have 3 different plot lines. So going through this, it took me a minute to figure out what the heck was happening down here. So I made some notes. So the first, think about these in sets of 3. So the, I think one is the array's indices are our x-axis. The y value is the second array. And then we have a descriptor of what that array should be marked like. So this first one is red hyphens. So you'll see this first linear is red hyphens. The second one is x-axis of t, y-axis of t squared, blue squares. And you can see blue squares. And the third one is, again, x-axis of t, t cubed of green triangles. Oops. So now I have green triangles on my cubed function. So we're starting to take the data we have in our array. These arrays are just being built with the arange and whatnot for convenience. As we get into data analysis, we will start looking at data over time from some sensor or from some whatever, and we'll get data over time. We can start plotting where we can have a time series on our x-axis and the value on the y-axis. We'll start to be able to figure out correlation between data, all that kind of cool stuff. And so now, but for now, we're just doing some basic plotting to show what the functions look like. I could plot any one of these. I don't have to plot all 3. In this case, it's just to show you that you can have more than one axis series, more than one series in one plot function call. So PLT is the matplotlib library plot function, and then at the end I have to show that, or I have a show function where it puts it up in this case in Jupyter Notebook as an image. But if you're writing a Python command line application like we've done, you can output these as a PNG file, as a JPEG, whatever. There are different ways you can store the output of this. Good? Ish? This is a fun example where I have a function I've defined which takes a parameter t and it returns the exponential value of negative t times the cosine value of 2 times np pi times t. It does some math. Maybe that's something cool. I don't know what it is. I have two arrays, T1, T2, with different values. And here I'm going to create two plots. So in Matplotlib world, this is a plot. The full XY axis graph is a plot. So here I'm going to create two plots, or creating a figure with two subplots. And the first subplot will have the x-axis values from T1. So we'll have three x-axis values. And the y-axis value is the result of the f function for each number. And a blue O for that. I'm going to have a second series on that plot with the other array, the T2 array, doing the same calculation, but they will be described as K, which all it does is change the color to black. Then I'll have another subplot where I take the T2 values, run them through a cosine function with pi, 2 pi the number, print out as a red line, and I get two charts with information. Any of you math nerds enough to figure this one out? What the heck it's doing? I mean, I know what the cosine value of a number does. Doesn't look familiar to anybody? Doesn't look familiar to me either. Anyway, what's that, Caitlin?
I haven't looked at anything like this since I was in high school.
Trying to think. Yeah, that was a long time ago. But the point of this one is to show that you can put every value through a function to get the values affected. We can do different kinds of charts. So these are all line charts or plot charts, whatever you want to call it. We can make a pie chart. So here I'm going to create a new pie chart where I'm plotting some number of students in different programming language classes, I think. Gonna have a students array as my first attribute. Then my keyword labels is going to be the languages in this case. Then we do some percentages, and I'm going to show that. So I can run this, and you can see now I have a pie chart sized as a relative percentage of the total. So you'll see C is 23 here. After calculations, that turns out to be 19.83% of the total. Python 25% of the total, which is our second to last one. So I can make a pie chart. I love visualizations too. Making data pretty is cool. But this should start giving you different ideas of if we start building dashboards or websites or whatever we want to do with all this data, we have the ability to dynamically generate charts and graphs. And when you smart business people are the CEOs of the company or the CTO of the company you work for, your CEO or board of directors will want pretty charts, and you'll yell at your employees and say, use matplotlib because you can. And it'll make you look smart. This one I threw in for fun because I really like the way it looks. I have no idea what these functions do, but it's got a whole bunch of stuff in here. And in the end, it makes a surface plot, which is kind of cool. But it's showing that we can do 3D charts instead of just 2D charts. There's an MPL toolkit library, an mplot3D package, where we can, I'm trying to find the use of that mpltd. Where is it? I don't actually see a use of it. I think it's needed because of that 3D projection. But we've got all kinds of parameters in here. This is our, I think the C map is a color map. So the value of the point on the chart represents a value of the color in this map. So we can change our color schemes based on different color maps if we wanted to. But here we have 3 axes. We have our x-axis, our y-axis, and our z-axis. And the values in there, I'm totally curious what they look like. I think I can do this. There we go. So we can print out a whole bunch of different, it's a whole bunch of different numbers. I should put a distinction between them, but we don't need to. But in the end, I got my plot, and that's the fun part. So this is something think about the visualization part here is really the introduction to data visualization with Python. The stuff to really sink in, like the details of from tonight, was all the stuff we talked about for the arrays. So before the fun visualization comment, everything before that is the arrays. And so getting comfortable with those will make your life a whole lot easier when we start dealing with the data sets, which we will do after our exam, I believe. And so on that, any questions before I reiterate what I said at the beginning about next week's exam? It's my favorite time of year. Not really. All right, I'm going